Okay, today we're talking 1.7, mathematical modeling and variation. So we're going to use modeling and regression to approximate sets of data points, and then we'll write mathematical models using direct, inverse, combined, and joint variations. So some of this hopefully should be familiar. You guys worked with bivariate data last semester in stats. I'm going to teach you how to create a linear regression, which is just a linear model that models these data points, and then we're going to make a decision on how well this model represents the data. So we're going to do this in Desmos. I went ahead and preloaded my table so you didn't have to watch me entering data points. If you don't know how to do this, to get a table going in Desmos, we go to the little plus sign in the upper left, hit that, choose table. And then you're just going to put your years, which are 2008 through 2015, in your X column, and then the population in millions in your Y column, okay? So your data should match mine. So this is the US population in millions by year from 2008 to 2015. Once you get that data entered, if you're at your standard here 10 by 10 window, you can't see any of the data points because they're way far away from here. It was always a struggle to teach students how to deal with this in the TI-84 because you have to manually adjust your window. Desmos now makes this much easier. If you see in my input box here in the lower left-hand corner, there's that little magnifying glass with a plus on it. If we just hit that, it'll take us right to the perfect window for viewing our data. And that looks pretty linear growth to me. So regression is coming up with a linear model that maps over that data as closely as possible. It's called a least squares regression. Again, TI-84, kind of a pain to teach because it's buried very deep. In Desmos, if you just click this little upper left-hand corner right below the plus, looks like a line going through data points, that's your regression. It'll default to a linear regression, which is great for us. I don't know if you guys got as far as discussing Pearson's coefficient, that's the lowercase r, or the coefficient of determination. But those are two values that basically give us how well our model fits our data. Basically, if r squared is almost like a percent grade of how well it does. So if we think of it that way, our line is doing a 99% good job of modeling our data, which is really good. This is a really good model for our data. Again, the nice thing is if we just click right above where it says statistics and residuals, it says equation. We can export that equation if we just click on it. And so I could use that if I wanted to make predictions, okay? There's a lot of times what we want to do when we create a regression, right? I'm just going to replace the y. I'm going to put it in function notation. Let's just call that f of x. And x is the year, and the output is, again, population in millions. So now I can make predictions. Let's say I wanted to predict, I don't know, the population in 2020. And this predicts 333 million, which is probably decent. Now, whenever you're making predictions outside of your data set, our data set only goes from the year 2008 to 2015. That's called extrapolation, and it's dangerous just because the further away you get, the less likely it is to be a reliable estimate, okay? But that's how to plot a data set, get a good window, and do a regression in Desmos. Okay, let's talk direct variation. So the statements below are equivalent. Y varies directly as x. Y is directly proportional to x. And y equals kx, where k is some non-zero constant. We call that k the constant of variation, or the constant of proportionality. So it doesn't always have to be y and x, and it won't always be y and x. But if you see blank varies directly as blank, it's going to be in this y equals kx sort of format. So let's try an example. All right. So in Pennsylvania, the state income tax is directly proportional to gross income. All right. So we have a couple different things. Here's our variable: state income tax and gross income. You work in Pennsylvania and your state income tax deduction is $4,605 for a gross monthly income of $1,500. Find a mathematical model that gives the Pennsylvania state income tax in terms of gross income. So right away, we see directly proportional. We're going to be thinking, okay, this is going to be in the form of y equals kx, although our variables don't have to be necessarily x and k. They can be whatever we want them to be. So for example, I'm going to call state income tax, let's call that S. And we'll call gross income G. Okay. Then S is directly proportional to G. That means S equals KG. So our goal here is to use the information. We want to solve for our constant of proportionality and then rewrite the model with that actual value for the constant in there based off of the information they give us. So the information they give us here is that our state income tax is $4,605 when our gross income is $1,500. So we're just going to take those values and I'm going to say, okay, so that means that when S is 4,605, G is 1,500. So I'm going to keep the K as K because that's what we're trying to solve for. All right, so now all I need to do is solve for K. Just divide both sides by 1,500. Simplify that. You can do that, pop it in the calculator, pop it in Desmos. We're going to end up with 0.0307. So there's the actual value for a constant of proportionality. And then the actual model is our equation, but with that constant plugged in. So it's going to be S equals 0.0307 times G. Now this is a modeling the relationship between state income tax and gross income. You could plug in any gross income and we could figure out what the state income tax for Pennsylvania is. All right, so direct variation as an nth power works the exact same way. It's just that our second variable is going to have some power on it, okay? So it's still in the y equals kx form. It's just x might have a power on it. Let's try one example of that. All right, so the distance a ball rolls down an inclined plane is, right away we see directly proportional. I'm going to highlight that, to the square of the time it rolls. Okay, so let's see. What are our variables? The distance a ball rolls is directly proportional to the square of the time it rolls. Okay. Well, let's come up with names for our variables. It's just called distance D. The square of time. Time is T, but the square of time is T squared. So again, directly proportional means, okay, it's going to have this sort of relationship, y equals kx. But in this case, D is directly proportional to the square of time, so k t squared. So there's our basic model. And now we're going to use our model to solve for k given the using the given information here. So let's see, what do they tell us? During the first second, the ball rolls 8 feet. All right. So that means when during the first second, so t would be 1, the ball rolls 8 feet. So the distance is 8. And so I'm just going to plug those values in for d and t. So 8 equals k times 1 squared. And We'll just go ahead and solve for k. Well, 1 squared is still 1, so we get k as 8. And now for part A, we're going to write an equation relating distance to traveled time. So this is our actual model. So this is just going to be d equals 8t squared. And on this one, in part B, they take it one step further and they ask us to figure something out using that model. So how far does the ball roll during the first 3 seconds? So d equals 8 times 3 squared, 8 times 9, which is just 72. And then we just want to put context on there. So notice that our distance is given in feet. So this answer is 72 feet, which you can see right here. All right. Okay, on to inverse variation. So the statements below are equivalent. Y varies inversely as x. Y is inversely proportional to x. And those both tell us that this is the relationship. Y equals k over x. Again, k is our constant of proportionality. So now instead of multiplying by our independent variable, we're dividing by it. So let's take a look. Company has found that demand for one of its products varies inversely as the price. Okay, so this is basic economics. So demand varies inversely as price. Just come up with variable names. Demand, I'm going to go D. Price, feeling creative, so I'm going to go P. All right. And again, right when we see varies inversely, we know we're talking about the form y equals k over x. But we don't have a y and an x, we have a d and a p. So d varies inversely as p, so d equals k over p. Okay. Now we're going to use the information they give us, again, to solve for k and actually write out a mathematical model for the situation. So when price is 625, the demand is 400 units. So that just means our P equals 625. The D is 400. Let's go ahead and solve for K. So 400 equals 625. No, sorry. Equals K over 625. And so we just need to multiply both sides by 625. Solve for K. That can go in the calculator. 625 times 400 is 2,500. Okay, so our actual model is D equals 2,500 over P. Okay, we're not done yet because they ask us a final question, which is approximate the demand when the price is 575. So now we're actually going to put our model to use. The demand is 2,500 over a price of 575. Plug that into our calculators, and we're going to approximate to the nearest whole unit. We get about 435 units. And there it is. Okay. So we got two more types. This one is combined variation. So this can have multiple types of variation going on at once. There's still going to only be one constant of proportionality. So let's take a look at this. So this is featured when some problems will have both direct and inverse variations. So a gas law states that the volume of an enclosed gas, so volume, varies inversely as pressure. So I'm just going to go straight to variable names here. We're going to call volume V. We're going to call pressure P. And right away, volume varies inversely as pressure means V equals K over P, right? Inverse is we divide by our independent variable. But then it says, and directly by temperature. Call temperature T. So direct variation is when we multiply by our independent variable. So it's now going to be times T as well. So that's both direct and inverse variation. And now, just like before, we'll just use the information they give us to go ahead and solve for our constant. So pressure is 0.75 kilograms per square centimeter. So that's, my P is going to be 0.75. Temperature is 294 Kelvin. So 294 for our T. And volume is 8,000 cubic centimeters. So V is 8,000. Okay. So we're just going to plug all that information in. So 8,000 equals K over, my P is 0.75 times my temperature is 294. Okay. So I need to isolate K here. So we're going to divide both sides by 294. I'm going to get 8,000 over 294 equals K over 0.75. And we're going to multiply both sides by 0.75. And that's going to be my value for K. Go ahead and pop that in the calculator, and that comes out to about 20.408. Okay, so now we're ready to answer A. We're actually going to write our equation that relates temperature, pressure, and volume. So V equals 20.408 over P times T. So there's our actual model. And B, find the pressure when the temperature is 300 K and the volume is 7,000 cubic centimeters. So this is 7,000. 20.408 over P times 300. All right, so this one's a little bit more unique in that the variable I'm trying to find is in the denominator, so I need to get it out of there. To do that, let's go ahead and multiply both sides by P. So that'll cancel these. And then I'm going to divide both sides by 7,000. So P is 20.408 times 300 divided by 7,000. Pop that in the calculator. We get 0.875. And then for units of pressure, we'll just go back up here and note that the original pressure they gave us was in kilograms per square centimeter. So that's what the units need to be on my answer, kilograms per square centimeter. All right. Okay. Our last type of mathematical model is going to be joint variation. So the statements below are equivalent. We say Z varies jointly as X and Y, or Z is jointly proportional to X and Y. And the equation that that's indicating is Z equals KXY, where K is some non-zero constant. And so this is just a situation kind of like combined, where we have multiple independent variables. So X and Y are variables. But Joint variation is always just straight multiplication. Okay, so it's almost like direct, just with multiple variables. And just like direct, your independent variables can be to powers, like the rolling ball example. So I could say z varies jointly as the nth power of x and the mth power of y, and that means z equals kx to the n, y to the m. All right, so let's do one joint variation example. This is for all you finance bros. We're going to be talking simple interest here. So we say the simple interest for an investment is jointly proportional. So right away, jointly proportional, we know that's z equals kxy form, although we might use different variables. So jointly proportional to time and principal, principal being your initial investment amount. Let's come up with variables. Interest, we generally go capital I. Time, we're sticking with T. And principal, I'm going to go capital P. Again, that's initial investment. So right away, I is directly proportional to T and P. So I equals KTP. Okay, something to know about interest formulas. T is always given in years. All right. So now we have our general model, but we need to solve for K using the information that they give us here. So we'll go ahead and do after 1 quarter, which is 3 months. Now note that that's indicating that my time in years, 1 quarter is 0.25. Okay. All right. The interest on a principal of 5,000. Okay, so principal P is 5,000. And I, the interest, note, is 43.75. So I is 43.75. Okay. A, write an equation relating interest, principal, and time. So we want to solve for K here. So I'm going to say 43.75 equals K times 0.25 times 5,000. To isolate K, just divide out the 0.25 and the 5,000. So I'm going to get 43.75 divided by 0.25 times 5,000. All right, which is about, if we pop that in a calculator, 0.035. Let's write our answer for A. If any of you, again, finance bros, can tell me what that 0.35 is as far as significance in this formula, it's actually just the interest rate of this account, 3.5%. Okay, so there's A. I equals 0.035 TP. And then let's go B. Find the interest after 3 quarters. Okay, so I equals 0.035. Our time after 3 quarters, that's 0.75 of a year. Our principal, I'm assuming, is still just the $5,000 we initially invested. Pop that in the calculator. We got $131.25. There we go. So that was mathematical model and variation. Go ahead and get started on your group work and your delta math.